Here we have a function e to the power 0.5x squared times the quantity 1 plus square root of 2 pi times the Gauss function of x. We'll generate the dataset of this function and its Taylor-Maclaurin series-sum expansion, where it is the summation of a times x to the power n, where a can be a1 or a2. And the value of n is from 0 to infinity. In this case, we can start from 0 up to 16, which is good enough. Now we calculate a2. Array formula 1 over factorial, double factorial of n. And we continue with coefficient a1, which is array formula. Again, factorial, double factorial of n minus 1 and minus 1 divided by factorial of n. That's divided by factorial of n. And we'll correct this so that if n equals 0, it should be 1. So that's if n equals 0. Equals 0, it should be 1. Otherwise, calculate. Now their values are exactly the same. We continue the series-sum expansion. Array formula. Series-sum of the x values raised to the power n, where n starts from 0, incremented by 1. And the coefficient, we can choose a1 or a2. We start with a2. And we'll chart this. So insert chart, and we'll use scatter chart. Use row 1 as header, series, trend line, polynomial to the 8th degree, the label, use the equation, the legend, position at the bottom. For the horizontal axis, number format, none. For the vertical axis, show the axis line. And the number format, none. Now we have enough space. So here we have the trend line and the polynomial to the 8th degree. So we continue with the function itself, which is array formula. And it contains the exponent, so exponent x times Gauss of x values. We need the polynomial of this and the trend line. So edit chart, customize series, trend line, polynomial to the 8th degree, and the label, use equation. We'll calculate the regression coefficient using LINEST. To do that, we complete the LINEST matrix. So we begin with the power. Transpose from 0 to 8. And the elements of the matrix. So array formula of the x values raised to the power 0 to 8. Now we calculate the polynomial regression coefficient using LINEST. Data y and data x. Those are for the expansion. Now the function itself. So LINEST, data y, and data x. Now we modify the function to match with the expansion, starting with the exponential form. So that is e to the power 0.5 x squared. So 0.5 times x squared raised to the power 2. Next, that's times the quantity 1 plus. So times the quantity 1 plus Gauss function. And in front of the Gauss function, you have square root of 2 pi. So this is 1 plus. You multiply square root of 2 times pi. Close the pi and close the square root. Now they're all same trend line. They're the same, exactly the same. Their polynomials are exactly the same. Their trend line is exactly the same, and the polynomials are exactly the same. We show this. We expand it a little bigger. Yep, they are exactly the same. So start from x to the 0, 1. Coefficient of x, 0.999. Coefficient of x squared, 0.5. Coefficient of x cubed, 0.339. Coefficient of x to the 4th, 0.126. Coefficient of x to the 5th, 0.0555. And coefficient of x to the 6th, that's x to the 5th, 0.0555. Coefficient of x to the 6th, 0.0182, 0.0182, 0.0182. Coefficient of x to the 7th, 0.0166, so 0.0166, 0.0166. Coefficient of x to the 8th, 4.28 times 10 to the minus 8, 4.29 times 10 to the minus 8, minus 3. Suppose we change this. Here we're using A2. Suppose I change this to A1. Delete. And now we'll use A1 as the coefficient of expansion. The values are still the same, the trend line. The polynomial is still the same. The trend line is still the same. The polynomials are still the same. The polynomial regression coefficients are still the same. This completes the use of double factorial and factorial in generating the Taylor-Maclaurin SERIESSUM expansion of this function e to the power 0.5x squared times the quantity 1 minus square root of 2 pi times the Gauss of x values.